To solve complex logic problems, the artificial intelligence industry currently relies on a single dominant strategy: inference time scaling. You see this in models like OpenAI's o1. When faced with a difficult prompt, the system is instructed to generate thousands of intermediate thinking tokens, writing out its internal logic step by step in plain text before finally outputting an answer. This chart compares the resulting hardware load. On the left, as the model emits linguistic tokens, the KV cache expands linearly. It consumes massive amounts of memory bandwidth, generating the necessary syntax, grammar, and vocabulary just to think out loud. This creates a structural bottleneck. Deep reasoning requires high-dimensional, continuous logic, but this methodology forces that logic to collapse into low-dimensional language at every single step. Eventually, the context window hits a physical memory limit and the reasoning chain breaks. Scaling artificial reasoning purely through the emission of language tokens is an engineering dead end. It hits a hardware wall long before it reaches deep deductive logic. Project B52, codenamed Ene v1.0, replaces linguistic reasoning with a mechanism called latent space recursion. Ene is a 1.3 billion parameter model. Rather than emitting text tokens to reason, it loops its hidden states continuously within a 2048-dimensional latent space. It can execute up to 100 internal recursive passes before it generates a single word. Because the reasoning happens internally, the KV cache remains entirely static. The computational burden shifts away from memory bandwidth and transfers directly onto internal matrix multiplication. The intended deployment hardware for this architecture is not a server farm, but an AMD Ryzen 8945HS APU. This orchestrator model is designed to operate locally within a strict low-power envelope of under 35 watts. Since each of those 100 passes sweeps through the 12-layer decoder, the 1.3 billion parameter orchestrator achieves an effective depth of 1,200 layers, reaching the deductive capacity of a massive server model without exceeding the VRAM of a laptop. If looping hidden states is so efficient, an obvious engineering question arises. Why not just take a standard transformer block and loop it 100 times? The answer lies in the spectral radius of the transition matrix. This chart tracks a continuous mapping applied to a single latent vector over 100 iterations. If the radius is greater than 1, the state explodes into infinity. If less, it collapses. Repeatedly applying the exact same layer causes tiny quantization errors to compound geometrically. The vector path shatters into a chaotic point cloud, a system killing, not a number error. Academic architectures, like deep equilibrium models, have tried to solve this by seeking mathematical fixed points using root-finding solvers. But when processing highly varied text, those models frequently fail to converge. To survive extreme recursive depth, a network must be engineered to actively perturb and catch its state, forcing the data into a stable reasoning orbit. Ene solves the recursive state collapse problem by replacing standard homogeneous layers with heterogeneous block cycling, specifically the ABC triplet pattern. Block A is the hypothesis block. While standard attention blends multiple meanings together, the hypothesis block branches the state into 4 distinct reasoning paths: translation, symmetry, rotation, and noise. The model then evaluates these options through a hard Gumbel softmax bottleneck. It executes an argmax selection, committing to a single logical branch. It does not blend math, it decides. This hard commit generates massive backpropagation shockwaves that would instantly throw an error and kill a standard network. That brings us to block B, the differential block. This layer operates as an active mathematical dampener, specifically designed to absorb those exact shockwaves. Block B executes noise cancellation by subtracting a local window attention map from a global attention map. This acts as a high-pass frequency filter, isolating critical symbols and forcing violent gradient spikes down to a stable baseline. Finally, Block C, the reflection block, reverses the standard attention sequence. By executing cross-attention before causal self-attention, the newly filtered state is anchored back to the facts of the original prompt before it can drift. This triplet mechanism allows the system to maintain a stable reasoning orbit. In tests with random, untrained weights, the system sustained 171 recursive passes without a single error, a process that collapses standard transformers in less than 5. But topological stability is only half the battle. During the scaling phase, an audit uncovered a hardware assumption that actively poisons deep reasoning: the industry's reliance on lower precision data types, like 16-bit or 8-bit floats, to maximize speed. If we track a single reasoning loop scaling past 100 passes using these lower precision standards, the math breaks down. The code casts data up to FP64, then truncates back to FP32, creating a precision yo-yo. Across 150 passes, 4,000 truncations introduce microscopic rounding errors. This accumulates into a massive noise floor that completely drowns out the model's 0.0005 convergence threshold. The result is a model that hits its maximum pass limit every single time. It mathematically cannot converge on a simple logical truth because the data is too blurry. The fix is absolute numerical rigidity. The residual stream must operate in pure, bare metal double precision, FP64, to preserve data integrity across the recursion. Standard lower precision formats cannot survive the compounding errors of deep deductive reasoning. FP64 is the only way to stop the latent bucket from leaking memory. Once the math is stable, the engine faces its final operational challenge: knowing exactly when to stop thinking. Instead of predicting standard end-of-text tokens, Ene relies on a specialized module called the verifier brain. Using attention-weighted pooling, it scans the reasoning chain for logical contradictions and generates a halt confidence score. If a query is straightforward, it achieves first-pass convergence. The verifier registers a confidence above 0.95, the gate snaps open, and the token is emitted immediately. Standard autoregressive models do not have this gate. They are bound by stochastic sampling, meaning if they lack the correct data, they are structurally forced to guess a word, creating a hallucination. Ene is trained on catastrophic failure trajectories to learn the opposite behavior. If the confidence remains low, even at the maximum pass limit, it triggers a latent deadlock. In a latent deadlock, the model is mathematically forced to abort. Rather than guessing, the orchestrator emits a zero-trust failure state, explicitly stating it cannot solve the problem. By replacing stochastic guessing with a rigid verifier gate, Ene becomes one of the first architectures inherently capable of absolute, zero-hallucination trust for mission-critical deployments. But a deadlock leaves the user without an answer. What happens to the query when the main orchestrator hits a confidence wall and cannot proceed? The 35-watt base model acts as a cognitive router. When it deadlocks, it packages the current latent state and routes the problem entirely off-node. It taps into a decentralized ecosystem of specialized expert nodes, isolated models trained as mathematicians, systems engineers, or physicists. These are fine-tuned weights equipped with rigid deterministic external solvers, like Z3 and SymPy, to verify proofs rather than estimating them. Offloading the heavy recursive mathematics ensures the main orchestrator remains unblocked. It delegates the complex problem and immediately pivots back to maintain real-time conversations with other users. This all returns to the foundational hardware constraint. The primary routing node, executing the internal loops and making the delegation choices, is running entirely on a local consumer processor. By decoupling reasoning depth from parameter scale and utilizing localized expert nodes, Ene moves high-level logic out of the data center and into a 35-watt envelope on a consumer desk.